Thank you for connecting. So today I'm going to talk to you a bit about the work we have done within the CO2 pipeline. First, I will give a brief intro of why are we looking at possibilities to reduce CO2 emissions from the steel industry. If we see now, every year in the world, we are producing more greenhouse gases. And if we don't stop with this increasing trend, we might reach a temperature, a super high temperature in the world that will have drastic consequences. So some studies have reached to some more realistic numbers where our adaptation could be easier to handle for the global warming, and this is to limit the temperature increase between 1.5 and 2 degrees. However, to reach these pathways, it's necessary not only to drastically reduce our emissions, but also innovate in the technologies that we use in the world. What are greenhouse gases and why do they increase the temperature? Well, most of them is due to CO2. We also have methane, and they accumulate in our atmosphere. And when we receive energy from the sun, it stays longer in our atmosphere, and that's why this temperature is increasing. I think one of the most logical ways to try to reduce this is to identify the points where these greenhouses are produced. And basically, they are produced in everything we do and need in our lives. Most of them are produced due to energy requirements, a quarter of it specifically for the industry sector, and actually 7% from the iron and steel industry. So that's more or less the motivation of why we are doing this kind of analysis. Now, let's talk about how is steel made. Steel is typically made from the removal of oxygen from iron ores, so this iron oxygen, with the use of a reductant, and normally this is coke. I will put my pointer. Yeah, so we use coke to remove this oxygen, we make CO2, and then we have the iron. Ideally and stoichiometrically, we will produce 0.6 ton of CO2 per each ton of iron that we make. However, this is not the case because this reaction doesn't take place at room temperature and it's thermodynamically limited. So in reality, this reaction occurs in a furnace that it's operating above 1000 degrees centigrade. And to reach this temperature, it's necessary to use additional carbon to burn it with oxygen, thus making additional CO2 that it's not producing the iron directly. And also the conversion of the coke is limited due to interactions between CO and CO2. So actually, 2 tons of CO2 are produced per ton of iron, which is 3 times more than the ideal one. How can we reduce this? There have been several approaches, but I will focus on those that require the use of renewable electricity. Now, many industries want to use electricity or green electricity to abate CO2. And I will say the demand is very high now to what we actually produce. And actually there have been studies like, for example, Power to Watt, where they analyzed what if we have only 1 megawatt hour of electricity, where can we have the largest impact to minimize the global warming, in which sector, in mobility, heat, power, fuel, or to chemical. And actually the largest impact was in the heat and the mobility sectors, while the chemicals are the lowest one, even though hydrogen is the highest of all of them. So why should the steel industry have a megawatt hour of green electricity if we could minimize the emissions in other sectors? Well, okay, maybe that's not the right question, but the idea of our study was to analyze actually how much electricity is needed, and if used in the future when we have much more availability of green electricity, how much will we be able to abate. So if we go back to the steel plant, here you have the furnaces that operate at high temperature, and from them we get a mixture of gases that consist mainly of CO2, CO, nitrogen, and some hydrogen. And currently they are burned in a power plant to make electricity for the steel plant. It also produces some excess of electricity, and then they are emitted as a CO2 nitrogen mixture. But what if we take these gases that still have some energy and we apply the carbon capture, utilization, and storage? In this case, the steel plant will not produce its own electricity. It will need a bit of electricity from the grid. We will use part of this energy to transform some CO2 into methanol, and the excess of CO2 will be simply stored. If we want to, or we are interested in actually making more methanol, in that case, we don't have enough energy. We will need more electricity to produce hydrogen to then convert all the CO2 to methanol. Or what if we rebuild completely the steel plant, we change the furnaces, and now we need an electrolyzer to produce hydrogen to remove the oxygen from the iron ore. So the point or the focus of our work was to analyze these three with the benchmark in order to have a conclusion of what could be the more effective way to use electricity in the steel plant. If we go back to the benchmark, this is more or less what I was explaining. So we have the gases that are sent to the power plant and burned. And note here that this electricity that is exported from the steel plant actually has a carbon intensity that is much higher than the carbon intensity of coal plants, which is already high, around 1 ton of CO2 per megawatt hour. And now we will do an analysis with the grid emission intensity of 0.25, which is much lower than the one that is produced in the power plants, and is actually similar to the one that we have now in Belgium. What happens with the CCUS scenario? Here we have the absorption enhanced water gas shift reactor, where we separate CO2 and we transform CO to hydrogen, and it's in the mixture with nitrogen. We recover the hydrogen, and as I said, we transform this hydrogen together with CO2 into some methanol, and the rest is stored. In this case, oh, and I forgot to explain the benchmark. So originally, as I said, almost 2 tons of CO2 per ton of steel are produced, and some electricity is exported to the grid. In this CCUS case, we reduce the emissions around half, and we need around 1.1 megawatt hour to still produce 1 ton of liquid steel, while storing 1.1 ton of CO2. If we don't want to store CO2, we need the electrolyzer, which will actually demand 8 times more electricity. And actually, with this grid emission of the electricity intensity, we produce more emissions than the benchmark. So actually, the CCUS scenario is not favorable when using not completely green grid. But in this case, all CO2 becomes methanol, and yeah, I'm just thinking why I have this here. Okay. The hydrogen-based steel plants, so we rebuild completely the steel plant and we only make hydrogen to remove the iron. And in this case, we need around half than the CCU scenario, which already makes it favorable. And with this electricity intensity, it already reduces emissions from the steel plant. This, I remember now, this 0.5 is the CO2 emissions that are avoided because methanol is now produced from CO2 and not from fossil sources. Okay, then if we put it in a Pareto plot, so we can see better the benefits that each scenario gives. We have the benchmark that it's near 2 tons of CO2 per ton of liquid steel with the electricity consumption in the bottom. We have the CCUS is the one closer to the left side because it needs the least electricity and it reduces 55% of the emissions. CCU requires the most electricity and doesn't reduce emissions with this carbon intensity. And the hydrogen-based steel making requires around half. What happens then if we, as the time progresses, the carbon intensity in in the grid decreases because we have more wind and more sun? Then also the electricity intensive processes will also reduce emissions, but even around 0.13, the CCUS scenario, it's more reduces more CO2 than the hydrogen base and the CCU. So since Jan already turned on the camera, I move to the conclusions. So for the CCUS route, we have a reduction between 50 and 70% of the emissions, only using 1.1 megawatt hour of electricity. And we don't need completely green electricity to achieve this. And also it can be implemented in the short term because it just requires an adaptation of the steel plants that we have now. It also provides some flexibility because the methanol reactor can be larger. So as surplus electricity is available, more or less methanol can be produced. The CCU scenario, on the other side, maybe requires too much electricity. But yeah, there can be a mixture between these two. And the hydrogen one reduces up to 85, same as CCU, and requires somewhat less electricity. The problem is that there is a lot of capital investment that has to be done to reach this scenario. So in conclusion, we either need storage capacity or renewable electricity if we want to reduce emissions in the steel sector. Thank you.